Alright, Assalamu alaikum. So today we're going to start looking at real systems, something that we're all familiar with, and these objects are called atoms. So atoms really combine together the concepts of quantum mechanics that we've learned so far. These structures that we call atoms are a nice test bed for quantum mechanics. You can test whether quantum mechanics works or not, how accurate is it, by looking at the behavior of atoms, the structure of atoms, and for that purpose you need to have some mechanism of talking to atoms. You need to control atoms, you need to harness their capabilities, and you need to measure atoms as well. You need to do microscopy of atoms, you need to observe atoms, you need to see inside atoms. And for that purpose, I've actually brought a demonstration in for today, which we developed here in our laboratory. But before that, I would like to talk about some background. First of all, we all know that we have a wave function in our real world, which is 3 dimensions of space and 1 dimension of time. We have these 4 variables on which the wave function is going to depend. And we also know that we have an equation which is called the Schrodinger equation, which applies at low speeds when particles are moving at slow speeds, which means non-relativistic speeds, speeds much smaller than the speed of light. So we don't have to worry about special relativity. And this equation, which we call the Schrodinger equation, helps us determine this wave function. But we need to know one thing, and that is the potential landscape. We need to know the potential contour. How does the potential change in space? So this is what we need to know. So we input a known potential inside the Schrodinger equation, and we solve the Schrodinger equation by some techniques, and lo and behold, the wave function results. And the wave function is important because the modulus squared of this wave function, which is also denoted by this notation, tells us what's the probability density of locating a particle, it could be an electron, inside an atom at some location. Now these coordinates x, y, z, these refer to the Euclidean axes. You have an x-axis, a y-axis, and a z-axis. So when we talk about atoms, and the simplest atom that we can talk about is the hydrogen atom. And hydrogen is not unimportant. Hydrogen is the most abundant element in the universe. About 99% of the universe is made up of hydrogen, of the known matter, of matter which we don't call the dark matter. The luminous matter is mostly made up of hydrogen, about 99%. So it's really an important element. Now, if you look at the hydrogen atom, there's a single electron inside the hydrogen atom around the nucleus. The nucleus just has a proton. So let's talk about atoms that are similar to hydrogen. And we would like to talk about single electron atoms. We just contain a single electron, and you can have more protons and neutrons inside the nucleus. For example, deuterium has a proton and a neutron. It has 2 nucleons. Tritium has a proton and 2 neutrons. So these are single electron atoms. You can also have the alkali metals like lithium, sodium, potassium, rubidium, cesium, francium, the elements of group 1 of the periodic table. These are not single electron atoms, but the valence electron. So if I look at sodium, atomic number 11, it has 11 electrons. but there's only one electron in the valence orbit. So that single electron sees, what does that single electron see? It sees a nucleus with 11 protons and 12 neutrons, and it sees 10 other electrons. So if I look at the sodium atom, and I just draw a cartoonic picture, don't believe these diagrams because now we are familiar with quantum mechanics. Everything is fuzzy. But let's, for a naive moment, consider this picture in which I have 2 electrons in the K shell of sodium, 8 electrons in the L shell of sodium, and a single electron in the valence orbit, in the N orbit. Now this is a naive picture, so keep that thing in mind. But this single electron that is further away from the nucleus, it observes, from its point of view, it's seeing 11 protons inside the nucleus, 12 neutrons, and it sees 10 electrons that are screening the nucleus, that are outside the nucleus and intervening between its own position and the nucleus. So there are 10 electrons in between. So this proton, this electron actually sees 11 positive charges and 10 negative charges. So it's actually seeing a single net positive charge, single positive charge. And it behaves as if it's just a single electron within a bigger nucleus, or a smaller charged nucleus, sorry. Because there are 11 protons in here, 10 electrons, which shield the effect of these 11 protons. So this electron just sees effectively 10 electrons. It just sees 1 proton, 1 positive charge. 11 positive charges inside here and 10 negative charges inside the K shell and the L shell. So it just sees 1 positive charge inside itself. And you can model this single electron by virtue of the single electron model. So the model that I'm going to describe is relevant to hydrogen-like atoms as well as alkali metals. Now, the first thing that we need to know is how do we figure out this potential here? There has to be some interaction. There has to be some force between the electron and the nucleus. That force is purely of electrostatic nature. It's a force of attraction. Let's suppose there is a single proton inside the nucleus of charge plus E. The charge on electron is minus E. Now, if I wanted to plot the potential V as a function of distance from the nucleus, what would this graph look like? What's the potential energy far, far away from the nucleus? 0. Alright? And how does the electron behave as it gets closer to the nucleus? Does the potential energy go up or down? It goes down because of the attractive pull of the nucleus. So it likes to spend its time close to the nucleus. They are friends. They are oppositely charged particles. So if I were to make a plot of the potential energy versus the distance from the nucleus, then this graph is going to look like something like this. Now, this graph actually has a mathematical form as well. Alright, one thing to keep in mind is that this is the distance from the nucleus. Does it also depend upon the direction? So if an electron is over there and I'm the nucleus, and if the electron changes its orientation, keeping the distance fixed, would the potential energy change? No. This is a purely spherically symmetric problem. There is spherical symmetry in this scenario, which means that the electron could have any orientation. It could be to the right of the nucleus, to the left of the nucleus, above the nucleus, below the nucleus. It could be at any angle theta, any azimuthal angle, any polar angle theta, any azimuthal angle phi. So the potential energy is independent of the orientation. It only depends upon the distance from the nucleus, which I call r. And it does not depend upon any other coordinate. Alright, so this r is really x squared plus y squared plus z squared under root. So if I have the nucleus over here, and I would like to find out the position of an electron, and I'm in three-dimensional space, no doubt, then I need to specify three parameters. The first parameter that I need to specify is how far is the electron from the nucleus. And that concept of fartherness is given by r. The other parameter that I need to define is, I need to define the orientation of the electron. The orientation requires two angles. The first angle is this angle, which I denote as theta, and I call this the z-axis. So I need to know if the electron is at theta equals 0, 90 degrees, somewhere in between, 45 degrees, 60 degrees, 75 degrees, 120 degrees. Where is the electron with respect to the z-axis? The point is that if you have a hydrogen atom sitting there, there is no z-axis. Keep that thing in mind. What axis will you call the z-axis? It's a spherically symmetric problem, so pick up any axis you like and call it the z-axis. Okay, there's no preference of which axis is particularly the z-axis. Pick up any one axis and then be consistent, call it the z-axis, and you're good enough. So I need to specify this angle theta. But then the electron could have any azimuthal angle as well. It could be in like this, it could be like this, it could be like this, it could have any azimuthal angle. So I need another angle. So what I would like to do, I would take a projection of the position of the electron on the xy plane, and then I could draw a line that connects the shadow of this electron. If it's being illuminated from the top, it forms a shadow on the xy plane. I connect this shadow to the origin, and this angle becomes my azimuthal angle phi. So I have three parameters, r, theta and phi. So instead of x, y and z, this distance of course is x squared plus pi squared plus z squared under root. But instead of specifying these Cartesian coordinates, it's better to solve this problem, look at this problem in another coordinate system in which I have three other parameters for r, the polar angle theta and the azimuthal angle phi. Okay, so I'm going to recast this problem in terms of these polar coordinates, as they are called. So this potential energy is a function only of r. It does not depend upon theta or on phi. Such a potential is called a central potential. Which is orientationally independent. It does not depend upon any orientation whatsoever. Alright? Now if I would like to write a mathematical form for this equation, that is simply going to be equal to V over R equals negative the charge on the nucleus, which is plus E, the charge on the electron, which is also E, negative E multiplied with E gives me minus E squared divided by a constant 4 pi epsilon naught, which comes out only because of historical reasons, divided by R. This is the potential energy. Now if I were to take the derivative of this, partial V over partial R, and put a minus sign with this, what are the dimensions of this object? It's a force. This will actually give me the Coulombic force between the electron and the nucleus. Okay? So this is the force, the electrostatic force between the electron and the nucleus. This electrostatic force is creating a potential energy. Just as if I'm lifting an object, the potential energy is going up because I'm lifting the object against a force of gravity. This gravitational field imparts a potential energy to this object which is dependent upon its height. Likewise, in this electrostatic case, we have pure Coulombic interaction between the electron and the proton, and that causes a potential energy distribution that looks like a well. So if I plot this in 3 dimensions, so what is this well going to look like? I have the x-axis here, I have the y-axis here. If the nucleus is located at the intersection of the x-axis and the y-axis, as I approach this nucleus, the potential energy is going to go down from all sides. So this is just like a whirlpool. The potential energy is just like an inverted Mexican hat, a sombrero hat. It's inverted, and the potential energy is going down at the location of the nucleus. So the electron would like to spend its time close to the nucleus, but actually it doesn't because of the uncertainty principle. If you try to squeeze the electron closer and closer towards the nucleus, its energy is going to go up because of confinement, the confinement energy. Now we have a form for the potential energy, and we would like to put this inside the Schrodinger equation and solve the Schrodinger equation. Yes, there was a question at the back.
So why would I have a negative sign with partial U over partial R?
Here? So this is how we define a force. So let me give you an example. If there are 2 planes, this is, and the force of gravity is pointing downwards. There's a force that is pointing downward, consider it to be gravity. Now if an object is placed here, it will have a certain potential energy. If the object is placed at a higher location, it's going to have another potential. Which one of these is greater? This one is greater. So the potential energy is going higher as you're moving against the force of gravity. So the force is pointing downwards, but the gradient of the potential energy is moving positive in the opposite direction. So the force is downward, but the potential energy is going higher and higher and higher as you move against the force of gravity. Okay, that's why we have this negative sign. The force is pointing in one direction, but this object is pointing in exactly the opposite direction. Okay, so if the force is, say, let's call this the z-axis. If the force is in the negative z direction, some f magnitude in the z direction, negative z direction, then the potential energy is going up in the positive z direction. Now I have to specify a direction as well. Let's call this direction z. So what's happening is the potential energy is going up in the positive z direction, opposite to this force. Okay? So potential V. I take the derivative of this potential Z and have a certain direction to it, Z. This is going to be the negative of this, because this is minus Z. If I would like to have plus Z, I would take the negative of this. This is this relationship over here. So this relationship is just presented over here. Okay? And this accounts for this negative sign. Alright. So now I have this potential energy term. I would like to plug it into the Schrodinger equation. What does the Schrodinger equation look like? The Schrodinger equation looks like this. Minus h bar squared 2m partial square partial x squared, the wave function x, y, z, t minus h bar squared over 2m partial square partial y squared x, y, z, t minus h bar squared over 2m partial square partial z squared psi x, y, zt plus the potential energy term which is given over there, which becomes minus e squared 4 pi epsilon naught r psi x, y, zt equals iota x, y, zt. Now you need to solve this equation. Now solving this equation is not as easy as the problems that we've already encountered. The first thing that we would like to do is we would like to stick to one particular coordinate frame. And the coordinate frame that we would like to stick to is the polar coordinate frame. So what we would actually like to do is, we have this wave function, and instead of using these coordinate axes, we would like to use the polar coordinate axes. So we would like to use r, theta and phi instead of x, y, z and t. Now if I know this r, theta and phi, can I calculate x, y and z and x, y and z? Yes. So the transformation between these coordinate systems is clear. Now what do I do about these terms over here? How do I cast these derivatives, this derivative, and this derivative in terms of r, theta and phi? Okay, so that's the problem. Now if you learn calculus 2 or advanced calculus, you'll come across problems of this kind in which you have to work in the polar coordinate system. In the polar coordinate system, these derivatives don't take up these simple forms. They take up more complex forms. So all three of these terms, minus h bar square over 2m partial square partial x square minus h bar square 2m partial square partial y square minus h bar square 2m partial square partial z square, they take up another form which I'm just going to write as minus h bar square 2m del square. So I'm going to represent all of this by this notation. Now this is just a new piece of notation. So don't be frightened of it. It's actually simple. I don't have to write all three of these terms over and over again. I can just write this thing. Now this thing can be expressed in terms of r, theta and phi. It can be expressed as double derivatives of r, double derivative of theta, double derivative of phi. But I can't just replace this x with r, this y with theta and this z with phi, because the relationship between x, y, z and r, theta and phi is not linear. If I were to look at this figure over here and I ask you to find out the relationship between x, y, z and r theta and phi, your answer will immediately be the following. X equals r cosine theta cosine phi. So the x coordinate depends upon the projection of r on the xy axis, which is given by r sine theta so this length is r sine theta, because this is r, this angle is theta, this length will be r sine theta. This angle is 90 degrees. So this is r sine theta. Now I would like to take the projection of this onto the x-axis. Since this angle is this angle is so this is r sine theta. This angle is phi. So this distance is going to be r sine theta into cosine phi. Let me draw this figure in a clearer fashion. I draw a sphere. I have a point somewhere here. This is my z-axis. This is my x-axis. And this is my y-axis. Now this point has some coordinates x, y and z. Now I define this angle to be theta. I define this distance to be r. Now what I could do, I could take the projection of this point on the xy plane, somewhere here. It falls onto the xy plane. Now if I would like to find out this distance, then I see that I have formed a right angle triangle. This angle is theta, this angle is theta, this distance is r, so the length of this segment is r sine theta. So this segment is r sine theta. Now I would like to find out how much x does this projection contain. Now if I look at this circle from the top, which means that this is my x-axis, this is my y-axis, and this point is now projected somewhere here. I know that this distance is r sine theta. If I would like to find out what this length is going to be, which is really the x coordinate of this point over here, then if this is r sine theta, this angle is 90 degrees, and this angle I find to be phi, then this length is going to be r sine theta, which is this length multiplied by cosine phi. So the x component of this point is actually r sine theta cosine phi. The sine theta projects this point onto the equatorial plane, and then I take the projection on the x-axis. If I were to calculate the y coordinate, this is the y coordinate. The y coordinate is going to be given by r sine theta sine phi. What about the z coordinate? If I look at this graph here, I would like to find out the z coordinate, this length here. What is this length going to be equal to? It's just going to be r cosine theta. So x, y, z, a point which has coordinates x, y, z, when it is expressed in the polar frame, all the coordinates get mixed up. You see, z depends upon r and theta. And it does not depend on a linear fashion. This is a trigonometric function here. It's a non-linear function. Okay? So r and theta mix up to give you z. Likewise, r, theta and phi, all three of them mix up, make a potpourri and give you y. All three of these coordinates mix up in trigonometric semblance and give you x. So all coordinates mix up to give you the polar coordinates. That's why these double derivatives with respect to x, y and z do not take up a simple form. They have to be derived. And the relationship is slightly complex. Now, when you plug in the forms for this operator inside the polar coordinates, you get a form of the Schrodinger equation. This operator here, by the way, is called the Laplacian. Can you please turn this projector on? Now let me show you what this Laplacian looks like. And I do not want you to solve this equation, but I would just like to flash the solution in front of you. I don't want you to understand the solution, it's not expected of you, but I just like to show you that once you have the potential energy function, the description of the potential energy, you can actually plug it into the Schrodinger equation, and you can solve the Schrodinger equation. You can find these wave functions over here. This is the goal of the problem. You want to find out these wave functions, just as you've done for the infinite well, the 2D well, the 3D well, the one-dimensional well, etc. Now let's look at the solution that I have in front of me. Any questions up to this point? Yes. Express? Use phi alone, because you need to know this distance. This distance is not the same as this distance. This length depends upon this theta. So if theta is smaller, then this is going to be a smaller length here. This theta is 90 degrees, this will be the entire length. So this length actually depends upon this theta, that's why. Alright, now look at the computer screen. So these notes have actually already been uploaded on the website. Now if you observe here, Ali, can I get a pointer please? So if you observe here, this is minus h bar square over 2m. I am representing m by mu. Why am I representing it by mu? Because generally the electron is much lighter than the nucleus in most cases. If you have a proton and a neutron inside the nucleus, the electron is much lighter. So when the electron is moving around the nucleus remains fixed. But that scenario might change. You can have just one proton inside the nucleus, as in hydrogen, or you can have an atom in which you don't have an electron but a heavier version of an electron called a muon. So if these masses become comparable, you have to take the reduced mass, but we're going to leave that aside, leave that point out. It's a minor detail. So this is the mass, or the effective mass of the electron. This is my Laplacian, which is a form in which I take into account the double derivative with respect to all three polar coordinates. And we're going to look at what this form looks like. this is my potential energy V. I'm calling it U in this write-up. And I'm just looking at the time-independent Schrodinger equation. I know that the time-dependent fluttering, or the wave function flaps its wings as Et over Hy. It continuously flaps its wings. But I'm just ignoring that for the time being. I'm looking at the time-independent part. So when I solve the time-independent part, I will just append it with this flapping term, the time-dependent term. So this is the time-independent Schrodinger equation, and we, like any other problem, we would like to use separation of variables. So I would like to have a function which I call the radial function R. Now this is really important. You need to understand this part. This is R. It depends only on R. Just as we've done for the two-dimensional well, for the three-dimensional well, for the one-dimensional well, we want to separate out the variables. Let's have a function that only depends upon R, a function that only depends upon theta, and a function that only depends upon phi. So we separate out this wave function, which we would like to find out, into these separate three independent parts. And then we would like to look at the definition of the Laplacian operator. This is what the Laplacian operator looks like. Isn't this inspiring? So it's not 1 over x squared, it's not 1 over y squared, it's not 1 over z squared. These complicated expressions make this Laplacian operator look more complicated. So now you have 1 over partial r into r squared partial over r acting on the wave function. Here you have, it is a double derivative of r. So 1 over partial r here, but slightly in a more complicated fashion. Here you have partial theta, partial theta. So again it's a double derivative with respect to theta. But notice that you have an r squared term with this as well. So even though these are derivatives with respect to theta, it has a 1 over r squared term. Likewise, this term is, there's a typo here by the way, this is partial square over partial phi squared. Okay, so this has to be a double derivative, this is a typo here. But it's conjoined with an r factor and a theta factor. So all of this is my Laplacian. Now I plug this Laplacian into the equation itself. I take this value of the Laplacian and put it in here. So I get this thing. So this Laplacian operator then acts on its predator, which is this function r theta phi, r theta phi, r theta phi, r theta phi, r theta phi. So I'm replacing the wave function with r theta phi. Now, in fact, even if you studied calculus 1, you should be able to do this derivative. You take the derivative. Now, when you take the derivative with respect to small r, theta and phi appear as constants. Here, r and phi appear as constants. Here, r and theta appear as constants. So you do this derivation, and then what you would like to do, you would like to divide both sides by r theta phi. This is the usual thing that you actually do. Okay? So you divide both sides by r theta and phi, and this is the relationship that you come up with. Okay? Now I multiply both sides, I do some algebra, and I get this thing over here. Now, this is something really nice. You can actually do all of this up to this point. It's not difficult. It looks difficult because it's lengthy. Writing down this equation would require probably 80 or 90 strokes of your pen, so it's longer, but it's doable. So once you do all of this, the algebra, this is the equation that pops out. Now look at this equation. I've reordered this equation a little bit so that on the left hand side, I only have terms in phi. only in phi. And on the right hand side, I have terms in r and theta, and they are mixed together. They are mixed together. Which means that if I varied phi alone, none of these terms is going to change. If none of these terms is going to change, then this term should not change upon varying phi as well. Okay, so this must be equal to a constant, and this must be equal to the same constant, because I've separated out the dependencies. This only depends upon phi, this only depends upon r and theta, but it turns out that this actually is independent of even phi. This is even independent of theta and r, because if I change phi a little bit, this term has the potential to change, whereas this right hand side cannot change at all, which means that this shouldn't change as well, because there is an equality. This means that this term is actually independent of phi as well. It's a constant. I call this constant minus ml squared. Okay? I can call it whatever I like. I call it minus ml squared. Now when this is minus ml squared, this term is also minus ml squared. Now I have this equation, which consider equation 2. Now I divide by sine squared theta, I get this form here. Do more algebra. Now we have something really interesting. The left hand side of this equation only depends upon thetas, and the right hand side of this equation only depends upon r's. So both of them must be equal to the same constant by virtue of the same argument that we've been belaboring over and over again. So this must equal a constant, and this must equal the same constant. I call that constant L into L plus 1. Okay, I can give any name to a constant. I call it L into L plus 1. Now when I have this, I get an equation in R which depends upon L, and this also depends upon L. Now L and ml square are two constants that I've introduced. Then comes the slightly difficult part. This equation, by the way, this equation, you should all be able to solve this equation at least. Can you tell me the solution of this equation? In fact, I can ask you to solve an equation of this kind in the exam as well. This is something they should be able to solve. We've seen many examples of this kind. So if I look at this equation, this is my equation here. Now I replace this double derivative with some constant, I call it d here, d square plus ml square equals 0, which means that the auxiliary equation is this one, d is equal to this. So my roots are plus minus I ml, and this is my solution, where ml could be positive and negative. This is my solution. So actually there are two solutions, as we know, plus I ml phi and minus I ml phi, but we'll cover the latter, these one, by allowing ml to run negative. So we're fine. So this is the azimuthal part of the wave function. This is nothing but the azimuthal part. So we have solved at least 1/3 of the equation. Just quite easily. We can comfortably solve 1/3 of the equation. Now the other two parts are slightly more complicated, and the interested readers, students, the brave souls can actually go through this derivation here. It's lengthy, but it's within our reach, it's within our grasp. So I encourage you to go through this solution. I'm not going to quiz you on this, because I get questions like this, what I'm going to be quizzed upon. But nevertheless, this is the polar equation, and I can solve this equation. So I know that the theta part depends upon L plus 1. I multiply by phi, I multiply by sine squared phi, I perform a substitution. Now this is the new equation that I get. I solve this. There's a furthermore here. I keep on solving it. Just derivatives, nothing else. Then since I have a substitution, I replace sine theta by z. Keep on solving it. Keep on progressing. I keep on propagating. Now I have converted this theta dependent equation into a z dependent equation. This was actually seen 3 centuries ago by Legendre. Now when Legendre solved this equation, this can be written in another form like this. I can propose a solution of this kind. So this is what comes out. This is what is transpiring. Easy so far. I propose a solution which is a power series. This is what I get. Okay? All of this has been done by human beings. So I get a formula. So I have some physical constraints. And finally, this is my solution for the polar part. And I can find out all the wave functions in this fashion. So the key idea that I would like to show you is that all of this is possible. And human beings do this. Scientists do this. Mathematicians do this. Physicists do this. So finally what we do get is our solutions. And what do the solutions look like? Let me show you the solutions, the overall solutions. The first thing to notice is that this is a three-dimensional problem and there are certain constraints on the system. In a three-dimensional problem, I should also get quantum numbers. How many quantum numbers should I get in 3 dimensions? 3. Those quantum numbers are called n, L, and ml. So the wave functions change with n, L, and ml. Okay? So this radial part of the wave function, this is given, these are the different solutions to the Schrodinger equation dependent upon n, L, and ml. So look at this solution, for example. R is the radial part of the wave function, a solution to the Schrodinger equation. Now this subscript 1 represents the value of n. This second subscript 0 represents the value of L. And it turns out this radial function is of course a function of R. And ml has nothing to do with this term. ml does not appear in the radial part of the wave function. And this is the solution. This is just a constant. E is for minus R over A naught. R20 is n equals 2, L equals 0. This is the solution. Again, it's an exponent, a decaying exponent. E is for minus R divided by 2A naught because n now is equal to 2. Here n equals 2, so it's e raised to minus r over 2a naught. Here r equals 3, so it's e raised to minus r over 3a naught. So this pattern is followed. You can actually remember this pattern in the wave functions. The other thing is that this exponential factor is being multiplied by some polynomial of R. This is a polynomial of R, a polynomial of R, a polynomial of R, another polynomial of R, another polynomial of R. So as n goes up, this is 3, this is 2 here, the order of the polynomial goes up. This has an R square term. This also has an R square term because of this multiplication. This is also R square. So the order of the polynomial goes up, which means it has more nodes and antinodes, but it decays faster. This is the pattern that we see in the radial wave function. We also see a pattern in the other wave functions. Okay, I'm going to talk about orbitals in a while, but there are the these are the theta and phi parts written together. Okay, and I'm going to explain this in a while. These are really important, and these are what we call orbitals. But the key point is that there are 3 quantum numbers, n, l, and ml, and there are wave functions, and it also results in the quantization of energy of the electron inside the atom. So we're going to take a 10-minute break, and I'm going to reconvene after 10 minutes. I'm going to show you a demonstration that actually verifies this quantization.